Hello all, welcome to this tutorial in which we shall discuss on the idea of unsupervised domain adaptation. Okay, so let's plunge in the idea of unsupervised domain adaptation using adversarial learning, also famously called as the UDA. Yeah. So now what is the problem statement here? See, you have your source domain, you have your source domain DS. Now we are dealing with a classification task here, now wherein which you have xi as well as yi for a given set of examples, and these are sampled IID from the distribution P source. And then you have data T, that is your target distribution, which only has the images which doesn't have the label, and this is from a distribution PT. Okay, so now what do I want? And then okay, in addition to that, we know that this PS and PT are not same. No, they are different distributions. So now what is that we want? Now we have been given DS and DT learn features such that it performs. Now we can perform the classification task. It performs well both on PS and PT distribution. Now, that is the idea. Now for this, now we take a simple data set. Now we take MNIST. Okay. And then we take one more data set, which is MNIST M. Now this MNIST M is a 3-channel database. It's a 3-channel data set. Okay. So, 3D means something else. So it's a 3-channel. Now MNIST is 1 channel. Okay. What happens in MNIST M is, now you have a number in the foreground and then there is a colored thing in the background. Okay. So now in MNIST, you just have the black and white images. So now what do we do to work with this? Now this also we convert into 3 channels. Okay. This anyhow has 3 channels. Okay. And then you try to extract the features using a feature extractor. And then by looking at those features, we will decide to which class it belongs to. Okay, and the features that we get now should be invariant. Okay, now it should be able to recognize MNIST also. Now it should be able to recognize the MNIST M also. Okay, now this is the idea. Now let's try to formulate it. Now I have a feature extractor. I have feature extractor to which you give X and X hat. Okay, from the source domain and then the target domain, you get FS and FT, the features pertaining to source domain and pertaining to the target domain. Okay, so and then using the critique network, now you should be able to differentiate between whether it is from the source domain or it is from the target domain. Okay, now we should be able to differentiate whether it is from the source domain or target domain. Okay, now this is similar to the idea of adversarial training that we have been doing. Now comes the interesting part, an additional part, which is the label classifier. We will use this label classifier, which takes the input of fs only. Okay, this is your label classifier hv. Now it will say ys. Okay, it will give you y now, which is p phi, now which is y given fs. Okay, it will be able to predict to which class does the input belongs to, now given the features. Now we train this only using the features of source. Okay, so and then during the inference we'll be giving the features of the ft. Okay, so that it should be able to tell the class of it. Now if my adversarial training has been done proper, my fs and ft now will be similar. Now because of which I'll be able to recognize the class of the target domain examples. Okay, now this is the idea. So now how will my loss functions will look like? Now let's try to look at that now. You have your phi star and then the w star are argmin with respect to phi and max with respect to w. Your expectation of from the source space log of dw of fs. Okay, this is the first term plus expectation with respect to the target space log of 1 minus dw of ft. Okay, now this is how you get your feature extractor and then the critique networks weight updation. Now how do you actually get your label classifier thing? Okay, now this label classifier, now for that, now we know that now we should be using a CCE of the actual labels and then what I'll be getting from my feature extractor. Now that means that now this will have, okay, argmin of phi as both. Now why? Now how do you get this fs? Now to get this fs, now you have to go through this phi network, the feature extractor network, right? So both the parameters are there. This, both of them is there. Okay. Now these are the two losses now that we will be looking into. So now it is evident from these equations that my feature extractor, the parameters that my feature extractor has, actually have two objectives. Okay. It actually has two objectives. Now what are those objectives? The first one is the adversarial objective. Okay. The first one is the adversarial objective. Okay. Now the second one is your classification objective. Okay. So what do you mean by your adversarial objective? See, the idea of your adversarial objective is, so now you should, the domain classification, now that is your critique network, the loss which it is having, now the aim is to confuse it, the critique network. So you have to maximize that loss. Okay, you have to confuse it, so you have to maximize. The classification objective is you have to minimize the source label loss. Okay, so these are the two objectives that we are here. Okay, so now let's try to understand here. Now we want our feature extractor. We want our feature extractor to make hard for the domain classifier, to tell whether it's a source or is it from the target. Okay, so now the gradient that comes, okay, the gradient that come from the domain classifier will be used to update the feature extractor. Now, this is known to us. Okay, the gradient that comes here is used to update the feature extractor. So now what is that we want to do now? Okay, now let's try to understand the flow of this. Okay. So now what we do is we flip. What do you mean by we take the reverse of it? We take the negative of it. We flip the gradient from the domain classifier when updating the feature extractor. Now, why do we do it? This is called as gradient reversal. Okay. Now, if we don't actually do it, okay. Now, what happens is if we don't do the gradient reversal, then the domain classifier gets really good at detecting the source. Okay, and the feature extractor learns just to get specific for the source. It will not be able to generalize well. So now what we do, we actually flip it up so that it doesn't do the job. Okay, now if we do not do gradient reversal, the domain classifier gets good at detecting source. Okay, and the feature extractor learns domain specific features. Okay, it learns domain specific features which will not be able to generalize. Okay, which won't generalize. Okay, now this will be the problem. Okay, so now let's try to put all of these things up into the code and see how this actually happens. Yeah, I have used all the necessary packages. Okay, now this is interesting. This transformation is what is interesting for us. Now, why? Now, because I am repeating this thrice, the same data, the one channel data which is there, I'm repeating it thrice. Now, why? Now, because my target data is actually a 3-channel data. Now, if I convert it into one channel, that will also work, but this is one more way. Okay, I'm converting 1 28 to 3 28 by repeating it thrice. Okay, so and then I have the mnist m data, and then I'm creating loaders for both of them. Okay, And this is how denormalize it. Yeah, we should be knowing it by now. And then I just printed some examples for you to just look at. Okay, this is the difference. Okay, this is MNIST M1. Okay, yeah, it has to be much more properly printed. But anyhow, so MNIST, you'll be able to see that now. Now I should be able to learn representations that are actually invariant for the domain. I should be able to learn it using MNIST, and then we should be able to work using the MNIST M. Okay, and then I have created the loaders for both MNIST and FMNIST. I'm calling it a source loader and the target loader. This is my feature extractor. Now my feature extractor will be a convolutional network. Okay, you can increase the depth of the convolutional network. That is also fine. Or if you want to use just the MLP, that is also fine. No problem. Now you're given an input. Now your image is the input. Now let's go back and try to understand the feature extractor. Now here the input for the feature extractors are images. Now from the images you get the features. Okay. So you have got the feature extractor, and then the label classifier. Now label classifier will get the features. Okay. Now both the source features and the target features will be of the same size, but it only take the source features, and then it will be able to say that to which class it belongs to. Now this is the label classifier. Okay. And then you have a linear layer, now finally, which is mapping to 10. Now why 10? Now because MNIST is a case in which you have 10 classes. And then you have your domain discriminator, which is your critique network, okay, which will take features from the source domain or from the source target domain, and then it will be mapping to 0, 1. Okay, so final linear will have 1, and then have this. And this is my gradient reversal method. Okay, now you can see it here. Now it has two functions, two methods. Now one is the forward and then the backward. See, okay. Now let's try to understand it from the backward. So whatever is the gradient output that you're getting, you're taking the negative of it. Okay, you're basically reversing it. And whenever you're in the forward propagation, now it will work as an identity. Okay, it will work as an identity function. Now that means that whether it is there or not there, the forward propagation will be unharmed. In the backward propagation, now whatever the gradient you get, now that will be reversed. Okay. What do I mean by that? Let me diagrammatically explain it. Now, you have a block, okay? You pass x to this, you get x out, okay? Now, this is your forward pass. In the backward pass, now if you pass y, okay, if you pass y, the output will be minus y, okay? So now in your forward pass, the values are unaltered. In your backward pass, the gradient reversal actually happens. Okay, now, this is the gradient reversal block now that we have written there. Okay, so now going back, let's see how all of them bring together. Okay, so now you have all your the instances of all your models, and then you have your criteria for the class discriminator has to be a CCE. Now, because it's a 10 class problem, so you cannot use BCE. BCE is preferably used for your 2 class problem. And then in your feature extractor and then the classifier problem. So you have your parameters of F, that is your feature extractor, and then the classifier, the label classifier C. All those parameters are put together, and then your discriminator, it's standalone. Now here it is interesting. Now how the training loop actually happens. Okay, now you put all of them in training. Okay, fine. Now here you are getting your target iterator. Okay, your target loader is there. Fine. Okay, you're creating a load, you're creating an iterator out of it. Okay, fine, good. So now you get things from your source. Okay, and then you put it onto the device. And then the next batch, now this is why I have put it in try and expect block is. Now you try, so the number of examples in the target thing now may be less than or more than what is there in the source. Now that means that you cannot directly take it like the way in which you take the source. Okay, so now you just need the same batch size. Okay, now if it is there, you just get it. Now if the loader, the number of examples has been exhausted, then you reinitialize it and then you get it. Now, for example, what do I mean by that? Now, let's say that in your target, you have only 100 examples. Okay. And then you have to take 30 examples in each batch. Okay. For one batch, you will take 30. In the other batch, you will take 30. In other batch, you will take 30. Now, for the fourth batch, you only have 10. Okay. So now if you just take it, now what happens is only 10 will come. Now that may not match with the size of the source. Now then you reinitialize it and then take 30 from there. Okay. Now that is the idea. Now then you put it onto the device and then you concatenate both of them. Okay. Now you pass both of them through the feature extractor and then to the label classifier, you only pass the source. Now that is the reason why you are taking only from 0 till now what is the size of it. Okay. Now first, okay, now to understand this, let's go back here. You passed both of them put together. Okay. You put together, you pass both of them. Okay. So now you will have your FS and then FT. Now I only want to extract till FS. Now from 0 till FS, I'll extract and then pass it through the label classifier is what I'm saying. Okay. Now you'll pass it through that and then you get your loss for the classifier. That is your label classifier. Okay. Now then what you will do? Now whatever features that you have got, you pass it through the gradient reversal. Okay. So now let's try to understand this. Now you have your feature extractor. You have got this. Okay. You have your feature extractor. And then whatever source features that you have got, you pass it through the gradient reversal thing. Okay. Now you pass it through the gradient reversal. Now since it is the forward pass, now what will happen is the output of this, now it will be same as that of what has been given the input. Now we have seen this. Now gradient reversal, now in the forward pass will just work as an identity form. You just send it out. Okay, fine. And then you get the domain labels. Now, if you want to get the domain labels, so what you will do, you just take the size of S that is the source, and then you put all ones. XT you put all ones, and XS you put all ones, and XT you put all zeros, and then that will be your domain labels. Okay, and then whatever is the output of this gradient reversal, okay, of this thing, whatever is the output of this, now that you pass it through the domain classifier. Okay, that is your D. Okay, that you pass it through the domain classifier. So now while it is passing, okay, now you have got it. Now the gradient reversal will work as an identity and then you get your outcomes. Now then when back propagating, now you get it here. And then here what will happen? Now here you will be reversing the gradients and then you will be passing up. Okay, the gradients will be reversed and then it will be passing through the feature extractor. Okay, so then you pass it through the D. Okay, and then you calculate. Now that is your BC loss, and then you update. There's the similar things. Okay, so and then yeah, I have done it for you. So I have done all of this. And then how do you evaluate your target now? Now finally post training, now how do you evaluate? Now you get your features. Okay, now you get your MNIST, you get the test data of MNIST M. This is, you are getting the test data. And then you put your feature extractor and your class classifier, both of them in the evaluation mode. And then you just take the test loader, you get the features and then pass those features through the label classifier. Okay. Now what do I mean by that? During inference, now what you will do, you take the test loader, you pass it here, you get the test, and then you pass it through the label classifier, you get its label. Okay, and so we have evaluated. Now we have got an accuracy of 75.8. Okay, now this is how we work with the UDA, unsupervised domain adaptation, by using the idea of the adversarial training. Okay. So now, in addition to that, we also looked into the FID score. So I just want you to give a rough idea of it. Okay. I just generated some from using DC GAN. I just generated some 1024 samples. Okay, and then what I'm doing is I have written the code for the computation of FID scores. Now, how do you compute the FID scores? Now, let's just go through this once, and then you can use this code as a standalone thing for calculating the FID scores in your coming things also. Okay, so now, yeah, so now the first thing is you take the pre-trained inception net. Okay, all those necessary libraries, and this is the pre-trained inception net on ImageNet 1K. I have just taken, and then I have chosen the sum layer. Okay, after 7C, if you look at the inception net thing, it will be clear. Now I have taken that as the, that is 2048. Okay, that as the representation. Okay, now there is no need to take it 2048. You can take it at anything in between. Now it will be a block. Now you have to flatten it up. That's all. Okay, I have taken it till the feature extractor. Any CNN network will have feature extractor and the classification head. I have taken it till the feature extractor. Okay, the outcome is 2048. So now I have taken this. This is my feature extractor, and then I have loaded the images, and then I have extracted the features from both of them. Okay, that's what we do, right? Take the ImageNet inception network, which is pre-trained on ImageNet 1K. Okay, and then you pass D-true as well as D-generated from this. Okay, you get some features, which is for Z-true and Z-gen. Okay, and then what do? You take the mean and the variance, the standard deviation of it. You calculate mu and sigma for both of them. Okay, similarly you calculate it for gen also, and then you calculate the FID score. Now how do you calculate the FID score? You subtract the mean and then take the second norm of it, and then you get the trace of it. Now both of them are scalars. Now you can add them. Now this will give you the FID score. Okay, now the same thing has been done. Okay, you can look at the calculations, and finally we have got an FID score of 39.23. Okay, now lower the FID score, now better is the image. Okay, now you take real image as well as the generated image path is given as input to this, and then the output is the FID score. Okay, you can use this as a standalone thing in the any generative model which takes the images as input, and then you can use it. Now this is there in your DC GAN collab notebook. All the notebook links has been shared with you. This you can take it as a standalone piece, and then you can work with it. Okay. Now with this we conclude today's tutorial, in which we discussed on unsupervised domain adaptation as well as the FID scores. Let's meet in the next tutorials. Thank you.